Welcome to section 3.3. We're going to take the things that we learned in section 3.1 and 3.2 and expand on that with the trigonometric functions and their derivatives. Keep in mind, our trig functions have a lot of rules and have a lot of identities. And it's really important that you are familiar with the identities and how to use them. I have just a few of them displayed here, and there's many, many more that we need to be aware of in order to simplify our answers. But these are the ones that seem to be used the most in this upcoming homework section. All right, first, let's look at some limits of trigonometric functions. In order to obtain derivatives of trigonometric functions, we first consider some important trigonometric limits. Specifically, we look at this first limit here. The sine of x over x as x approaches 0 is equal to 1. And our second limit that we want to keep in mind is the limit as x approaches 0 of cosine of x minus 1 divided by x. And that, if we look at a table of values in a graph, is equal to 0. Another tool that we're going to use as we get moving here is the unit circle. Remember how the unit circle works. Each one of these ordered pairs gives us the cosine value of the angle for the x-coordinate, and then the sine value of that angle as the y-coordinate. So, for example, if I wanted to find the sine of pi over 3, here's pi over 3, and I would just say, okay, pi over 3 happens to be 60 degrees, and if I want to find the sine of pi over 3, that's going to be the y-coordinate, which is the root 3 over 2. Let's start with the basics, shall we? The derivative of the sine function, if we have sine of x, is going to be cosine of x. And the derivative of cosine of x is negative sine of x. We can prove that these derivative formulas are correct using the limits from the previous page and the sum and difference identities of sine and cosine. Let me know if you'd like to see those written out, and I can definitely do that with you. Let's look at our first example. Let's find the derivative and simplify. So if I'm going to find why is it not writing well? The derivative of y with respect to x, or dy dx. I need to keep in mind that I have to use the product rule, don't I? So here's my first function and my second function. And remember that if I'm going to find y prime, or the dy dx, I'm going to do the first times the derivative of the second plus the derivative of the first times the second. So the first function, f, that's just going to give me my x squared. And then I need to multiply that by the derivative of sine of x. And then remember, product is plus. And then I'm going to take the derivative of my first function, and I'm going to multiply that by my second function. Okay, so x squared, just going to use x squared. The derivative of sine of x, that, according to our rules we just learned, is the cosine of x. So it's going to be x squared cosine of x. Then again, remember, product plus. And I'm going to take my derivative of x squared. The 2 comes down in front, and I reduce the power of x by 1. And then sine of x is just going to go along for the ride. I can't really simplify that anymore, so I'm going to leave this answer like this. The only thing I might do, is if I needed to solve it, then I might factor out the x, 1 power of x, but that's it. Either of these final answers are acceptable. This one's a little bit longer. We have to use the quotient rule. So remember the quotient rule. In fact, let's write that down. Y prime is going to be my low d high minus my high d low all over low squared, where this one's my high and this one's my low. All right, so my low is this entire bottom. So I have 1 plus the cosine of x in parentheses. And then I'm going to multiply that by the derivative of the top. Then I'm going to subtract from that. And I'm going to take the regular of the top and multiply that by the derivative of the bottom. And I'm going to put that over the bottom squared. Now let's simplify. This just goes along for the ride. The derivative of the sine of x is the cosine of x. And I've got my minus. And then sine of x just goes along for the ride. And the derivative of 1 plus cosine of x, I have to take the derivative of both pieces. The derivative of 1 is 0, so I leave that alone. The derivative of a positive cosine is a negative sine. Not writing that very well. Just going to rewrite that as. Now, whole thing's going to be over that denominator squared. All right, so let's combine some terms. What I'm going to do is I'm going to distribute out this cosine of x, and then I'm going to multiply these two things together in the numerator. I'm going to leave the denominator alone. Remember, I leave the denominator alone. Especially if it's already written out in factored form. All right, just a reminder, I'm writing these functions as squares. If I have a trigonometric function squared, I write it in between the trig function and the argument. But when we do stuff later with it, not in this problem, keep in mind we can also write it like that. Okay. Well, now let's do a little bit more simplifying. We have an identity that we can use. We know that cosine squared of x plus sine squared of x gives me, 1. So this cosine goes along for the ride. These cosine squared and sine squared adding to each other creates a 1. And then down here stays the same. But now notice, even though they're in opposite order, I can rewrite it and see that the denominator and the numerator have a factor in common. So I can cancel the 1 plus cosine of x on the top, and I can cancel one of my powers of 1 plus cosine of x on the bottom. And now I'm done. There's my derivative. This is a fun little example. Let's say I wanted you to find the 27th derivative of the function cosine of x. It helps to write out a bunch of derivatives before guessing what the 27th derivative is. Also, I am not going to take the derivative 27 times. No, ugh, that's tedious. That's not a labor of love. That's just abusive. So let's go ahead and do it. Let's see what happens. So my first derivative, the derivative of the cosine function is negative sine. So then I'm going to take the second derivative. In the second derivative, I'm taking the derivative of the sine function. So the derivative, the negative sign goes along for the ride, and then the derivative of sine gives me cosine. Now let's look at the third derivative. So the derivative of cosine is negative sine. So a negative sine creates a positive sine. Then let's take our fourth derivative. Remember that notation we learned in last section. It has a little 4 in parentheses above it. Now we're going to take the derivative of the sine of x, and that's going to give us cosine of x. For the fifth derivative, and I'm not done yet, I'm going to do quite a few of them. The derivative of the cosine of x is negative sine of x. And then the sixth derivative is going to be negative cosine of x. The seventh derivative is going to be the positive sine, dot, 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 dot. Well, what you may notice is that we have a pattern that starts to repeat itself. So basically, the first derivative is the same as which other one? Yeah, the fifth derivative. And the second derivative is the same as the sixth derivative. Now, does that pattern hold true? Yeah. So if I have the first derivative, if I add 4 to it, I get the fifth derivative. So this would also be true for the ninth derivative. And then 9 plus 4 is 13 for the 13th derivative. And then the 17th derivative. And so on and so on. So this one here would be the same as the 10th derivative, the 14th derivative, the 18th derivative, and so on. And so the third derivative, even though we don't have this one written down, what's 3 plus 4? Yeah, 7. So in here we're going to see this would be the same as the 7th derivative. And then the fourth derivative, this would be the same as the 8th derivative. Now, how do we use all of that to figure out what the 27th derivative is? Like basically, we have four options, right? It's either negative sine of x, negative cosine of x, positive sine of x, or cosine of x. Well, if I look at my options here, I can definitely say, okay, it's not going to be this pattern here for f double prime, or the 6th derivative, or 10th derivative, or 14th or 18th, because these are all even numbers, right? So it's not going to be that. And then same with this one. I didn't continue this pattern, but this is going to be the 12th derivative, the 16th derivative, and we're looking for the 27th derivative. So it's not going to be that. So it's either going to be the first derivative relative or the third derivative relative. So if I keep adding 4 to these, which one's going to take me to the 27th derivative? And yeah, it's going to be this one. So my 27th derivative of the cosine of x is going to be equal to the same as the third derivative. Neat, huh? We have other trigonometric functions, as you know, and these are the formulas for them. I want you to notice something, that these derivatives, every time you have a cofunction, and I'm going to write the other derivatives on top here. When I had the derivative of sine of x, that gave me a positive cosine of x, right? And when I do the derivative of the cosine of x, I got the negative sine of x. Now you have to have these formulas memorized for the test that you're taking. But notice all the cofunctions are negative. So whenever you take the derivative of a cofunction, the derivative is negative. And whenever you take the derivative of a not cofunction, so sine, tangent, secant, those are going to be positive. Take the derivative of cosine, cotangent, cosecant. Those are all negative. Now again, we have some proofs that we can use. We're not going to do them. If you want to see me do them, I can definitely do them in another video or during a Zoom meeting with us for class. But for the derivative of the tangent of x, because a lot of students forget that square, it's actually not too difficultly, I didn't say that right, it can be derived without too much issue. If I say, okay, if I'm going to take the derivative of the tangent of x, a good way to try it is to rewrite the tangent as the sine over the cosine. And then use the quotient rule. So I've got the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Oh, I lied. I said I wasn't going to do it, but I am. I guess I'm just going to do it quickly. Notice what happens at the top. I end up with cosine squared of x plus sine squared of x. And in the bottom, I've just got this cosine squared of x. On the top, I've got that Pythagorean identity. Cosine squared of x plus sine squared of x, that equals 1. So this derivative is like saying 1 over the cosine squared of x, and that, my friends, is the secant squared of x. So all of these derivatives have fabulous explanations, but we're in the section of not doing our derivative rules the long way. It's just a simplifying afterwards that takes a bit. Okay, next example. We are going to use the Pythagorean identities. Specifically, when we're simplifying, remember the main Pythagorean identity is this one, cosine squared of x plus sine squared of x equals 1. And I don't know if a teacher ever taught you this, but if you take this function, if you divide every single one of them by the cosine squared of x, you end up with 1 plus the tangent squared of x equals the secant squared of x. And then if you take this original function again, and this time divide it by the sine squared of x, and you get the cotangent squared of x plus 1 equals the cosecant squared of x. And those are your Pythagorean trig identities, which are super useful. My chair is squeaky. Sorry about that. All right, let's do the derivative. Now, once again, you've got something divided by something. These aren't limits anymore, folks. We can't just take the derivative of the top and the derivative of the bottom. We have to use quotient rule. Okay, we have to use the quotient rule. And just remember the quotient rule, right? If it helps, write it down every stinking time until you have it memorized. But use that low d high minus high d low. All over the bottom squared we go. Or, you can just memorize it with the math speak style. All right, so my low is going to be that tangent. My high is going to be that 1 minus secant of x. So I'm going to start off with the tangent of x. Then I'm taking the derivative of 1 minus secant of x. Quotient formula says I subtract. And then I take the 1 minus secant of x, and I'm going to multiply that by the derivative of the denominator, which is tangent of x. And I'm going to put that all over the tangent of x squared. All right, well, let's do it. Tangent of x is just going to go along for the ride. Nothing special happens yet. The derivative of 1 minus the secant of x, so I take the derivative of 1, which is 0. And then the negative here in front of secant is going to go along for the ride. So I've got a negative. And then the derivative of the secant of x, look at those formulas, is the secant of x times the tangent of x. Next, I'm going to write my minus. And this part just goes along for the ride. And this one, when I take the derivative of the tangent, it's going to be the secant squared of x. And then that is all over the tangent squared of x. Okay, I will say this. There's a couple different things you can do. I've done this problem a few times, so I know what's the fastest way, but what I'm going to do is I'm not going to show the fastest way. I'm going to show the way that I would normally do it if I had no clue what's going on, all right? Because, well, frankly, whenever we're seeing new problems, that's how we often attack it, right? So the first thing I would think to myself is, ooh, I'm going to use the distributive property / just multiply the stuff that I need to multiply. So this thing right here I'm going to multiply that together. I don't use a distributive. It's just property. It's just a straight multiply. But this first one's going to turn into negative secant of x times the tangent squared of x. And then I've got minus. And then here, I'm going to distribute that out. It's a minus in the front, so either distribute the negative along with the secant squared or distribute the sign afterwards. It's up to you. But this is going to turn into the negative secant squared of x plus the secant cubed of x. And that's all over the tangent squared of x. Now at this point I may look at this and I may just think to myself, yuck. What am I going to do now? Well, darn it, excuse me. What I'm really going to do is I'm going to look at these three things. I'm going to think to myself, well, what can I do with this? And it may not seem totally obvious, but notice how each one of those terms has a secant in it. So what did I just do? What just happened? Okay. Anyways, as I was saying, these terms here all have a secant in it. So I'm going to factor the secant out. And then nothing fabulous really is going to happen. I'm just going to be able to factor out one, but maybe the stuff that's left I can do some simplifying with. And actually, I can. So remember I was talking about the Pythagorean identities before. If I use this Pythagorean identity right here, if I take the secant squared minus the tangent squared, so if I take the secant squared minus the tangent squared, those two combine to give me 1, right? Because secant squared minus tangent squared gives me 1. So I can cancel those and stick a +1 in there. So the secant just goes along for the ride. These two terms disappear and I replace them with a 1. And then in the denominator, I've got the tangent squared of x. And there's nothing else I can do with that. Think of these problems as a lovely little combination between, calculus derivatives and proving or simplifying trig identities. Right? Not for the faint of heart. Okay, so for what values of x does the graph of f of x, which is x plus 2 cosine of x, have a horizontal tangent? Well, let's remind ourselves, what's a horizontal tangent? Well, a horizontal tangent happens when we have a minimum or if we have a maximum or if we have some type of leveling off happen in the original function. So to get an idea of the solution, let's graph it. So when you graph it at first, it might not look too bad. Say, okay, we definitely have a maximum here, so there's going to be a horizontal tangent there. And then we look right here, we got a minimum here. So this is going to be a horizontal tangent there. But, you know, as we know, graphs go on forever and ever on men. Let's see what's happening at the end behavior. So let's zoom out a little bit. And holy cow! If you look at it, we got maximums and minimums everywhere, right? Everywhere. How exciting. So what we need to do is find all those solutions. Now, keep in mind, if we keep zooming out, we are going to find infinitely many solutions. But that's not our answer. We have to find out which ones they are. So let's do that. I'm going to keep a little unit circle handy so we can see what our solutions are going to be and what it is we got to do. All right, so horizontal tangent, as you know, is for a max or a min. And also, remember, that's when the derivative, the first derivative, is equal to 0. Okay, that's where you have horizontal tangents, when the first derivative is equal to 0. So we have to find the first derivative. So when I take the derivative of x, no problem, 1. Take the derivative of 2 cosine of x. So the derivative of 2 is 2. The derivative of cosine of x is negative sine of x. So my first derivative is going to be 1, and then 2 times negative sine x is negative 2 sine of x. All right, well now we need to find out for which x values f prime of x is equal to 0. We're looking for the slope of the tangent is equal to 0. So I'm going to take my 1 minus 2 sine of x equals 0. And then I'm going to solve this for sine of x. So I'm going to subtract 1 from both sides. And then I'm going to divide by negative 2. And basically, I want to figure out, where does the sine of x give me 1/2? Okay, and you can use the unit circle. You can also use your calculators. You can also say, oh, this is like saying the inverse sine of 1/2 gives me x. But there's going to be a few answers that we're going to put in here, right? In fact, remember, infinitely many. So let's see what we have for a pattern there. So for this, if you remember what I was talking about earlier, it goes cosine of x for the x coordinate, sine of x for the y coordinate. So starting here at 0, I want to look for where the sine is 1/2. Found it. It's 1/2 at pi over 6 first, so I'm going to write that one, pi over 6. And then nope, 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 yes, 5 pi over 6. And then nope, 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 nope. That's it. And notice, these ones are like close, but no cigar because it's a negative 1/2, so nope. And then this one is 2 pi plus pi over 6, because remember, when we look at revolutions, here we go, here's my full 2 pi, and then I keep going and going and going forever and ever, amen, right? So the next iteration would give me 13 pi over 6. And the next iteration of that, or the next one, it's going to be 17 pi over 6 for when I hit this one again. So basically it's when I hit pi over 6 or 5 pi over 6. All right, well, let me erase this and let me do some demonstrating. Okay, so my answers are basically found here. And anytime I cross this, so I find a solution here at pi over 6, and then I find a solution here when I go all the way around, 2 pi plus pi over 6. That's how I got the 13 pi over 6. And then I find it again when I go around again and do it right. So basically, my answer is going to be pi over 6 plus, and each time it's one revolution, let's say 2k pi. And then specifically, k is an element of the integers. Okay, it's like a funky little z. Z for Zahlen, because Gauss did a lot of stuff with integers and he was German. The other angle in question for our answer here is this 5 pi over 6. So 5 pi over 6, I get there here just starting at 0, and then going all the way around 2 pi plus 5 pi over 6, da 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 da. So this is going to be 5 pi over 6 plus 2k pi. And again, we already know that k is an element of the integers. So those are my answers. Notice that those two angles there, they're not related, right? They're not related by pi or by pi over 2 or anything fancy. So that's why you have one answer here, one answer here, and then you just do the plus 2k pi, because each answer after that is one revolution around. So let's look at a summary of these derivative formulas. Notice we haven't done anything with the chain rule yet. We haven't done anything super crazy, but you do still have to have these memorized. So these formulas here, you want to have them memorized so you can find the derivative each time, no matter what they give you. Additionally, we've got these derivative formulas for the trig functions that we just learned. Remember, these are when the argument, that thing on the inside of the trig function, is a simple little x. Okay? In other words, it's an argument where the derivative with respect to x of that argument is just a nice little 1. That's important because later on we look at what happens when arguments and powers and all that stuff are something other than, the derivative of it is something other than 1. And that's called the chain rule. But that's not until the next video. So in the meantime, work on your trig stuff, practice your identities, and have a good time. Find a nice window to have a seat by, and work on your math. Good luck.